good to see you again. Our prior video talked about finite dependence, which broadened the class of models to which we can apply the Hotz-Miller CCP estimation. However, there's been a critical assumption that we've been making, which is that we can observe all of the relevant states for our problem. And today we'll tackle what happens if we can't observe all of the relevant states in our model and what we can do about it as it relates to the CCP estimation method. And what we're going to see is that we need to incorporate finite mixture models and the EM algorithm, which we covered in a prior video series, to fully leverage the power of CCPs for our model. And just as a reminder, CCPs work because we can observe choices in the data as a function of the states. If we have two state variables, x and s, and we want to know what's the CCP for some value little x and little s, we can just estimate the probability non-parametrically by just counting how many observations were there that had this combination of x and s, and also made choice j, and then divide that by the total number of observations that had values of little x and little s. This is why we call it a conditional choice probability, because we want to know what's happening conditional at a certain point in the state space. And we use these choice probabilities, these CCPs, to construct future value terms like we've talked about in prior videos in this series. And we can leverage terminal choices or renewal actions or finite dependence to eliminate the backwards recursion problem. And the reason we can do that is because these CCPs are going to inform us about the value of taking a particular action at a particular point in the state space. So then this brings up a problem of what if some of these states are unobserved? We can't compute probabilities from the data if we don't have data on them. So mathematically, let's assume that state S is unobserved. How do we compute this probability? And this is a quite common problem in dynamic discrete choice models, either from dynamic selection or from serially correlated unobservables. For example, persistence in preferences or persistence in other aspects of the model. And so the paper that we're going to review that introduces this tool that will get us around this problem of not being able to observe the states is this Econometrica paper from 2011 by Peter Arcidiacono and Bob Miller. And the solution that they point out is that we can assume that the unobserved state S is finite, and then we can use the EM algorithm to basically treat this unobserved variable as observed and use that to form choice probabilities, and then we're back in business with the regular CCP stuff. So we're going to assume that there are capital R unobserved types that have probabilities pi s in the population. And the key idea is that we can use this posterior probability from the EM algorithm, the QIS that we talked about in a prior video. We can use that as a weight in our estimation. So this QIS is derived from Bayes' rule. Basically, I'm taking the population probability as my prior, and then I'm updating my prior based on my individual likelihood that I'm of type S, and that's just the formula for what that is. So this is a posterior individual level probability that I'm of type S, given everything I can see about me in the data and through the lens of my model. So then we just tweak this formula for the CCP to be weighted by the QIS terms. Now we have basically an observed value of this unobserved variable that is accounted for with the weights, and this allows us to estimate CCPs for unobserved states. And just as a refresher for the EM algorithm, we covered this in a prior video, but it's helpful to review it here. We start with guesses for our parameters of our likelihood function, our utility function parameters, and the population probabilities, and hence the CCPs. And then we use those to update the Qs. So we get a new version of Q. Maybe the original Q, we can just start at the pi for that, for everyone in that type. So that's the E step update will give us the new Qs, and then the M step update will give us the new values of our parameters, the new thetas and the new CCPs based on the updated Qs. So again, we're weighting all of this stuff. And why is there two separate things here? Well, because we have a two-stage estimator where in the first stage we get the CCPs. In the second stage, we estimate the flow utility parameters given those estimated CCPs. So everything is weighted in the M step. And then the E step just basically updates the weights. So what are the benefits of this approach? Well, we don't need to fully solve the model, and we can handle unobserved states so long as we have either finite dependence or renewal or terminality in our model. The M step of the EM algorithm is going to treat these types as observed and just weight the estimation by those type probabilities. And we also get additive separability if we have other parts of our model, like we talked about when we introduced dynamic selection. We might have like an outcome equation in our model as well as a choice equation, and we can have additive separability in those components, which simplifies things. And so we maintain this computational tractability despite having unobserved heterogeneity in the model. And then just as an aside, there's an alternative where we can update our CCPs using the structural model instead of the weighted empirical frequencies. So we can use the likelihood of the model to update the CCPs, or we can just use a pure data-driven non-parametric CCP estimator, or we can use something in between the two. So there's a lot of options for how we want to update the CCPs, and they're all going to converge to the same estimates because it doesn't really matter the exact functional form of those CCPs for consistency of our econometric estimator. So that's just another thing to kind of know about how to apply this method. I don't know of a formal paper that's proven what I just said. It might be interesting to write that paper and compare and contrast different methods of updating the CCPs to get a sense for, maybe a machine learning algorithm could be better than either the structural model or the fully non-parametric approach, for example. And then another thing to kind of keep in mind is that when we're doing these multi-stage estimation procedures, we're going to have to bootstrap to get the standard errors of the structural parameters that we're after, because each stage introduces estimation error into its estimates. And so given that we're taking the prior stage's estimates as given and pretending that they're the truth, we're ignoring that estimation error. And so the standard errors can either be deflated or inflated depending on the degree of correlation between the errors across the different parts of the model. In this video, we showed how to overcome the limitation of unobserved heterogeneity in the CCP approach. However, there's still an Achilles heel, which is that we may not be able to use them, or in general, we can't use CCPs for policy experiments. And we'll talk more about that in the next video. So I hope to see you there.